There's always so many things to, now we're live. Okay, good. You can be sure that you always miss one button that you have to click.
Yeah.
Okay, and then let's record this. All right, so let's get started. Welcome everyone to today's meeting of the InfoSec Research Group. And it's my pleasure to introduce Andrew Lewis-Pye from the London School of Economics. He's a professor in the Department of Mathematics at LSE. And prior to joining LSE, he was a Royal Society University Research Fellow at the University of Leeds and a Marie Curie Fellow at the University of Siena. And his main research interests have been in computational theory and algorithmic randomness, but he has also worked in fields like network science, statistical mechanics, and population genetics. And his most recent research passion have been cryptocurrencies, and his talk today will also be from the space of cryptocurrencies, titled Consensus in the Permissionless Setting. And with that, Andrew, the stage is yours.
Okay, thanks very much, everyone. Thanks for coming. Thanks to Philip for inviting me. I'm being told that my internet connection here is a little bit unstable. So if it starts cracking up, and let me know, and I'll try and solve it by moving rooms or something.
Sure, sounds good.
That might be difficult because I've just moved into a new flat. It's a bit of a building site, but anyway, if it's a problem, I'll try and figure it out. Okay, yeah. So I'm going to talk about cryptocurrencies. So from a computer science perspective, cryptocurrencies are really interesting as consensus protocols, right? So Bitcoin is really a consensus protocol that can be used to instantiate a currency, but could also be used for lots of other things too. And in fact, so consensus protocols have been extensively studied in distributed computing since at least the 1980s. So what's new about Bitcoin, though, is that it's a protocol that operates in a permissionless setting. Now called the permissionless setting, which means you have a fixed set of participants, one of whom are unknown to each other from the start of the protocol execution. Okay, so maybe there are 10 of us, we all know each other are, and the protocol tells us how to interact so to achieve a certain goal. So what differentiates Bitcoin from those previously studied protocols is that it operates in a permissionless setting, which means that it's a protocol for establishing consensus over an unknown network of participants that anybody can join with as many identities as they like. Okay, so Bitcoin then is one form of permissionless protocol. It's called a proof of work protocol because it uses these hard computational puzzles to help us reach consensus. But then there are other more recent kinds as well. So there's also proof of stake protocols and proof of space protocols, and maybe there are other kinds as well. So then the existence of this new form of protocol brings with it all sorts of fairly obvious questions, right? So is there anything sort of fundamentally new happening here? Does the old theory basically carry over, maybe with some small sort of tweaks, or do we have to develop an entirely new theory here? How much can you do with these permissionless protocols and so on? So the main aim of this talk is going to be to introduce a framework for analyzing permissionless as well as permission systems that Tim Roughgarden and I have developed for talking about these things, which allows us to address all those questions. Right? Okay, so I'll very roughly describe the framework, and then I'll talk about some of the results we get using the framework. Before I do that, though, it's probably not that interesting to compare the new theory with the classical theory without knowing a little bit about the classical theory first. So in fact, what I'm going to divide the talk into roughly two parts. Okay, in the first part, I'm going to give a brief introduction to the classical theory of permissioned consensus protocols. Okay, so we'll talk about permission protocols in the first part, and then we'll go on and talk about permissionless protocols in the second part of the talk. Okay. Okay, so I changed my slide here. So the structure of the talk is basically as follows, just as I was just saying. So first of all, I'll talk a little bit about the classical theory. Okay, then I'll go on to briefly sketch the framework, and then I'll talk about some of the results we get. Okay, so let's do the permissioned case first. Then, right? So if we study the problem of reaching consensus and a more And there are various ways we can do that, but the way it's most generally used is due to Lamport, Shostak, and Pease. And they phrased the problem in terms of a group of generals of the Byzantine army camped outside an enemy city. Okay, so this is a quotation from the original paper. So we have a group of generals of the Byzantine army camped with their troops around an enemy city. Communicating only by messenger, the generals must agree upon a common battle plan. Okay, which you can think of being maybe either attack or retreat, something like that. Okay. However, one or more of them may be traitors, and we get into which. One or more may be traitors who will try to confuse the others.
Oh. Okay, I think we lost Andrew.
So my connection went at some point there.
Yeah.
I'll try and move rooms to see if we can make things a little bit better. Yeah, okay.
Sounds good. And maybe I will also turn off the video for myself.
Okay.
To like reduce the bandwidth requirements.
So I don't know, this room will be better. Okay, as I said, it's a bit difficult around here because I've got a building site. Sorry, just get this straight. Okay. Okay, so at what point did I cut out there? Was that right at the start? How much?
The last thing we saw was the Byzantine generals slide.
Right. Okay. So let me share screen again. Let's go to. There we are, and play. Okay, so perfect. I'm going to assume you didn't see any of this slide then. Okay, so we'll start from there again. Okay, so
we saw this one, yeah.
You saw this slide. Okay, so yeah. This is the basic problem as originally described by Lamport, Shostak, and Pease. So obviously this is a fairly sort of vague version of the problem. So now let's make that slightly more precise. Okay, so what we're going to do, we consider a set of n processes. Okay. Some of which may be faulty, and we don't know which ones might be faulty, right? It's important that we don't know which processes might be faulty here, otherwise I think it's going to become trivial because we can just ignore the faulty processes. And being faulty here could mean a number of different things, but for now, we're going to assume that faulty processes can display arbitrary behavior. Okay, so the non-faulty processes will carry out whatever protocol we tell them to. The faulty processes can display arbitrary behavior, and as you'll be perfectly used to, we'll generally assume that all the faulty processes are going to be controlled by a single malicious adversary who's going to behave in a nasty way in order to try and stop our protocol working. Okay, and then there are a number of different ways we can set things up here, but the way we're going to do it is as follows. Okay, so we're going to imagine that one of the processes is referred to as the commanding general. Okay, so we've got the commanding general and then all the other generals. And the commanding general could be faulty or could be non-faulty. Whether they're faulty or not, though, they're going to send an input to each of the processes, right, which is going to be either 1 or 0. Right? You can think of either as being attack or retreat. Okay, so the commanding general, if they're non-faulty, then they're going to send the same input to all the other processes, right, either all 1 or all 0s. But if they're faulty, then they might send different messages to different processes. Okay, so that's the conditions on the inputs there. And we have a couple of conditions on the outputs. Okay, so first of all non-faulty processes, well, first of all, they must output, and then they must also give the same output. Okay, so far that's trivial, right? Because they could just ignore their inputs and always just output 0 or something like that. But then we make it non-trivial with the next condition. So if the commanding general is non-faulty, then they'll give the same input to all processes. And in that case, all the non-faulty processes must give that common input as their output. Okay, so these are the two conditions on the outputs, yeah? Okay, so if the commanding general is non-faulty, he'll give a bit of the same input, and then all the non-faulty processes have to give that input as their output. Okay, so I guess this is one of those problems where you have to sort of think about it a little bit to convince yourself that it's not trivial, right? I guess the initial reaction is some sort of easy majority vote thing might work, but in fact it ends up being highly non-trivial, depending on the form of communication and how reliable communication is. So let's make that precise next. So this is the sort of classical formulation of the problem, right? So here we're in the permission setting. So we've got a fixed set of participants, all of whom are known to each other. So in picture here, obviously we have 6 participants, each node is a participant. And in the original formulation of the problem, each pair of participants has a private channel, a private communication channel between them. Okay, so each edge here is a private communication channel. And what we're going to imagine is that at each stage of the process, each participant can send a message, any message they like of any finite length, along each of their private communication channels. Okay, so we're going to imagine that time proceeds in time slots. We start time slot 0, in time slot 1, time slot 2, and so on. And each time slot, each participant can send any message they like of any length, any finite length, along each of their private communication channels. Okay, and then each participant also has a name or identifier, and these are all known from the start of the protocol execution. Okay, so here the identifiers are U1 up to U6. And then we might allow the use of digital signatures, or we might not. And generally, that's going to change what's possible. Okay. And then there are a couple of possible, there are more than a couple of possibilities, but I'm going to focus on a couple of different possibilities for the purpose of this talk in terms of how long messages take to arrive. So first of all, if we're in the synchronous setting, okay, if communication is synchronous, what that means is that for some known bound delta, some finite bound delta, messages take at most delta many time slots to arrive. Okay, and generally, okay, you can, if you like, to simplify things, you can just imagine the delta is 1. So if we're in a synchronous setting, then messages will arrive at the next time slot, if you like. Okay, just imagine delta is 1. So if I send a message at time slot 2, it'll arrive at time slot 3. Okay, that's the synchronous setting. And then there are maybe at least a couple of different versions of the partially synchronous setting. So one way to formulate it is as follows. So in the partially synchronous setting, again, so now delta still, there still is this bound delta, but now delta is unknown. Okay, and that ends up, for most purposes anyways, being essentially equivalent to a setting in which you have sort of sufficiently long synchronous intervals, but you also might have intervals in which you have some unbounded network partitions, right, in which the bound delta doesn't hold, but you don't know when those intervals are. Okay. Okay, so that's synchronous, and then we have partially synchronous. Then you could consider harsher settings. So in the asynchronous setting, messages will always arrive, but there's no finite bound on how long that delta arrive, for example. Okay, so that's the basic setup, right? So you have each participant receives an input. If those inputs are mixed, as they are here, then the only requirement is that all the non-faulty processors give the same output as each other. So here they could all output 0, or they could all output 1. If all the inputs are the same, well, then all the non-faulty processors have to give that same input as the output. Okay, and as I say, I guess, yeah, so this is one of those things where you have to sort of play around to make sure that it isn't trivial. So an obvious idea would be that just some sort of basic majority vote thing might work here, right? So you might think, well, if everybody receives their inputs, what we should do is just, we've received our inputs, tell each other what our inputs are, and then do some sort of majority vote. So that won't work. So let's just, first of all, make it entirely clear as to why that is. Basically, that's because the faulty processors can tell different things to different non-faulty processors. Yeah. Okay, so let's consider a simple example. So here we have 3 different processors. Okay, let's imagine that one of them is faulty. That's the top guy here. So these 2 are non-faulty. And these are input 0, 0, and 1. Okay, so now they're going to try out a majority vote thing. Well, then what does this guy here see? Well, it depends obviously what the faulty processor tells him, what he decides to tell him. So let's suppose initially that the faulty processor decides to be honest. So he tells him that he's input 0. In that case, what this guy sees here is 2 0s and a 1. Right, he sees his own 0, then a 0 and a 0, 1. So we're doing majority vote, he'll output 0. So next thing, what does this guy see? Well, now let's suppose that the faulty guy lies. So he sees 2 1s and a 0. So he's doing majority, but he's going to output a 1, right? So now we've got 2 non-faulty processes. This one's outputted 0. This one's outputted 1. And so the process hasn't worked, right? And in fact, you can show that there is no process which will work without digital signatures if you have one faulty processor amongst the 3 processes. Okay, so then, so what are the results? Well, so if n is the number of processes, then a basic question we can ask is, so how many faulty processes T can we handle? Yeah. And then the answer will depend upon the setting we're working in, right? So whether we have synchronous or partially synchronous communication, and whether we have digital signatures or not. So, with authentication means with digital signatures here. Okay. So first of all, if we're in the synchronous setting, so remember that means that messages, you can just think of that as meaning messages arrive at the next time slot, if you like. If we're in the synchronous setting and we don't have digital signatures, then the perhaps surprising result is that you can get a protocol to work even only if strictly less than a third of the processes are faulty. Okay, so maybe that's slightly surprising because you might think, that maybe a majority of the processes being non-faulty might suffice or something like that. But anyway, so we can do a working protocol. To have a working protocol, we require strictly less than a third of the processes to be faulty. If we have digital signatures, so with authentication, well, then we can handle any number of faulty processes, but there's no really trivial solution because if we have too many faulty processes, then T+1 rounds of interaction necessary. Okay, so that's for the synchronous setting. And then for the partially synchronous setting, which if you remember means, well, one way of saying it is that there is a bound on how long messages take to arrive, but you don't know what it is. So here again, so maybe there's some slightly surprising results. So now it doesn't matter whether or not you're allowed to use digital signatures, at least in terms of the resiliency, at least in terms of how many faulty processes you can handle. So now you can get a working protocol, even only if it's strictly less than a third of the processes are faulty. Okay, so of all of those results, I guess the proofs get harder the more sort of you move towards the asynchronous setting. So the simplest one by a long way is this result here. So if you have digital signatures, then you can handle any number of faulty processes. So what I'm going to do now is just to briefly sketch that result. Okay. Okay, so this is what we're trying to show. So we're in the synchronous setting here. Right, so we have digital signatures. We're trying to show that any number T of faulty processes can be handled. Okay, so let's suppose there are T faulty processes, and let's suppose that delta is 1. Okay, so that means messages will be delivered the next time slot. Can I just check for my piece of work? Can people hear me clearly when I'm in this room? Is everything okay?
Yeah, that's much better now.
Okay. Okay, so we'll suppose there are T many faulty processes. We're supposing delta is 1. So what's the basic idea here? Well, a really simple way to proceed might be as follows. So if we're working in the authenticated setting, which means we have digital signatures here, that's the terminology used in distributed computing. In the authenticated setting, the command in general can sign initial inputs. Okay, so generally we don't have to pay attention to inputs if they're not signed by the command in general. So it seemed a simple approach would be just to have processors propagate all the signed inputs they see, like maybe over multiple time slots. So basically, if ever I see a 0 signed by the command in general, I'll tell everybody else about it. If ever I see a 1 signed by the command in general, I'll tell everybody else about that too. Okay, maybe we do this over multiple time slots. Okay, and then ultimately we have them output Z if the only signed input they see is Z, outputting some default 0, 0 otherwise. If I see 2 different values, then I'll output that value. Again, I guess the basic idea might be, well, okay, so if the command in general is honest and he's only sent out 1 value, then we'll only see 1 value. So we'll output that value, so things will be correct. If he sends out 2 different values, well, then hopefully we'll see all those 2 different values, so we'll all go to the default if we're non-faulty. Okay, so the idea is, so maybe this will work. So what's the problem there? Hopefully the problem's fairly easy to spot. The problem is when's the cutoff, right? So if we stop listening for new values after X many rounds, well, then the adversary can just wait until that last round, right? When it's too late to tell people about what he's doing. You can wait for that last round and they can show some non-faulty processes 2 different values at that round, while others have only seen a single value. Okay, and if he does that at the last round, it's too late to tell other people about it. Okay, so what's the solution then? So here's a brief sort of sketch. Well, what we do a similar sort of idea, but we tweak it a little bit. Okay, so we consider messages signed by sequences of distinct participants. Okay, so for Z and 0, 1, I'm going to let Z subscript U1 up to UI. So these are different identifiers here, different names for different processes. Okay, so let Z subscript U1 up to UI be Z signed by the commanding general and then by U1 up to UI in order. Okay. And then just simple little definitions. We let MI be a set of all messages of the form Z subscript U1 up to UI such that all the U1 up to UI are distinct. Okay, so these are the messages signed by the commanding general, then I many other distinct processes. Okay, so that's just a couple of simple definitions. So now what do we actually do? As I say, it's fairly similar to the previous basic idea. So what we do is in times.i+1, we instruct processes only to listen to messages in MI. Okay, so we're going to imagine that the commanding general is going to send out his inputs at time.0, which means that at time.1, processes will listen to messages in M0. They'll listen to messages signed by the commanding general. Okay, but then at time.2, they'll only listen to messages that are signed by the commanding general and another processor. Okay, at time.3, they'll only listen to messages signed by the commanding general and two other processors. Okay, and we'll say a processor sees the input Z at times.i+1 if they receive a Z relevant form in the relevant MI. Okay. And then whenever a processor sees a new input value, what they're going to do is they're going to add their signature to the message and then send out that new version of the message to everyone. Okay, so for time.1, I see some message M0, that's just input signed by the commanding general. Then I'll sign that message, right, in order to form a message M1, and I'll send that out to everybody so they'll then listen to that at the next time slot at time.2. Okay, and then basically we proceed that way until round T+2. So around T+2, we're going to allow that people can receive messages. That's their last chance to see new values, but they're not going to send out any new messages at times.T+2. Okay, so at times.T+2, require then processors should output, and they output basically using the rule that I said before. If you've already seen one value, then you output that value. If you've seen two values, then you go to the default value, which is 0. Okay, so why does that work? Then we'll, okay, so first of all here, we're just recalling the output rule, like I said. Okay, so recall that non-faulty processors output Z if the only input value they see is Z, and output the default value 0 otherwise. So what that means is it suffices to show that one non-faulty processor sees Z, even only if they all do. Right, so either they all just see one value of Z, in which case they output that value, or they all see two values of Z, in which case they go to the default. Okay, so it suffices to show this fact. It suffices to show that one non-faulty processor sees Z, even if they all do. So why would that be true? Well, there are two different cases here. So first of all, the easy case. So note first that if a non-faulty processor sees Z strictly before times.T+2, right, well, then they sign it and they send it to all of the processors, right? So then all the other non-faulty processors see that value Z at the next time slot. Okay, that's the easy case, and then the apparently slightly more tricky case. So what happens then? So if a non-faulty processor sees Z at times.T+2, the last one, where it's too late to tell anybody about it, well, then what that means is by definition, by our definition of sees, right? By definition, that means that the message they see is in MT+1. Okay, which means that it's signed by T+1 distinct other processors. Right, but we only have T many faulty processors, so one of those processors must be non-faulty. Okay, so then that non-faulty processor will have propagated the relevant message in an earlier time slot, and so again, it'll have been seen by all non-faulty processors. Okay, so we get what we want either way. Either way, we get that one non-faulty processor sees Z, even if they all do. Okay, so that's the brief introduction to the classical study of permission systems and consensus and permission systems. So now let's move then on to the the permissionless setting. So in order to formally define the permissionless setting, we need some sort of framework. But first of all, let's do it informally. So what are the differences now? So I guess the first major difference now is that processes aren't told n. They're not told the number of other processes involved, and they're not told the identifiers, the names of other processes. Okay, that's the first main difference. Then the second difference, which maybe in some sense comes out of the first difference, is that now we're going to imagine that communication is by broadcast rather than having these private communication channels. Okay, so now if I want to send out a message, I have to broadcast it to everybody. And again, so if we're in the synchronous setting, then there'll be this bound delta, which everybody knows. And that means that when I broadcast the message, everybody else will get it within delta many time slots, but it might arrive at different users at different time slots. Yeah. And that kind of comes out of this first change here, basically, because if I had a private communication channel to each of the processes, then I could see how many people I'm talking with, right? So if we don't know n, then it doesn't really make sense to have a private communication channel with each of the other people I'm carrying the protocol out with. Okay, so communication now by broadcast. And then another difference is, so there's now no bound on the number of identifiers controlled by the adversary, right? So there's now no bound on the number of faulty processes. Okay, so basically in Bitcoin, well, I can use as many identities as I like and behave in a naughty way. Okay. Okay, so what changes now in terms of what's possible? So I didn't prove it before, but I did mention it briefly when we were discussing the permission case, that if we have T many faulty processes, then T+1 rounds of communication are necessary, right? So if the adversary can now participate with as many faulty identities as they like, then certainly it seems that consensus should now be impossible, right? So clearly, we're going to need to limit the adversary's ability to contribute in some new way. Make for a silent big part. Okay, so Bitcoin does this by assuming some limit on the computational power of the adversary, right? So we assume that the faulty processes together control less than half the computational power of the network in a way that we can make precise. For that reason, it's called a proof of work protocol. And I don't want to spend any time going into the specifics of how Bitcoin works, but very roughly, so Bitcoin uses this assumption on the adversary, right, that they have less than half the computational power to repeatedly solve the Byzantine generals problem. Basically, it can be thought of as solving a version of the Byzantine generals problem for each transaction, right? So for each transaction, either it ends up being thought of as valid or not. Okay, Bitcoin, though, only gives a probabilistic solution, right? And later on, I mentioned a result of ours, which says you can't have deterministic solutions to the Byzantine general problem in the permissionless setting, right? At least as long as you're reasonably strict about what it means to be a permissionless protocol. Okay, so you have to go to probabilistic solutions. Okay, so now then let's just very roughly sketch the framework. I don't want to get bogged down in the details. It's a fairly simple framework, but there's only so many details you can go through in a talk. Okay, so I'm only going to describe it at a very high level. Okay, so in proof of work protocols like Bitcoin, it's a participant's computational power, which decides their level of participation. Okay, and there are other possibilities, right? So in proof of stake protocols, it's the amount of currency owned which determines your level of participation. Okay, so users are randomly selected to produce blocks. And you're twice as likely to be selected if your currency balance is twice the amount. Okay, then there are also proof of space protocols, virtual memory capacity that matters, and other possibilities. Okay. So in all of these cases, though, there's some sort of notion of a limited resource and a resource balance for each user, which might vary during the protocol execution, right? And which determines your capacity to participate. Okay, so what we want to do is to define a framework which allows us to prove general results protocols that follow from simple properties of the relevant resource and the way in which that resource determines user participation. Okay, so the idea is we don't want to prove results that are specific to proof of work protocols and then finally have to constantly adjust the proofs to apply to other forms of permissionless protocol. We want to prove results that hold for all future forms of permissionless protocol, so long as they share certain basic attributes. Okay, so at a high level then, here's the setup. Okay, so we consider protocols which run relative to what we call a resource pool, this is just a function, which determines a resource balance for each user over the duration of the protocol execution. Yeah, I don't necessarily want you to get too hung up on the precise technical details here, but basically R, which is this is the resource pool, right? This can be thought of as specifying as a resource balance. The resource balance could be some real number. For each identifier, right? So for each name of each processor or each user, if you like, at each time slot, possibly relative to a given message state. Okay, so the message state here you can just think of as being a set of messages delivered to the user. So the set of blocks of transactions, we talk about Bitcoin. Okay, so it specifies a resource balance, a real number, for each participant at each time slot, possibly relative to a given message state. Okay, so a resource pool, but then we also have to determine how the resource pool dictates the ability to participate. So then we also have what's called a permitter oracle. Okay, so we stipulate that processors can only broadcast once permitted to do so by the permitter oracle. To gain permission, they submit requests to the oracle, who then responds depending on their resource balance. Okay, so obviously to make all that precise, I'd have to tell you the precise form of requests and the nature of the permissions given by the permitter oracle and so on. All that stuff's important, and that's all the stuff that is important. That's the stuff that's hard to get right. Okay, but for now, I don't want to go into all that detail. I just want to keep things at a high level. Okay, so far then, hopefully that sounds reasonably simple, but a bit vague. So a resource pool, which determines the balance for each user over the protocol execution, and then a permitter oracle that gives permission to broadcast depending on a resource balance. So I say that might sound a little bit vague, but hopefully it's clear how you might use this sort of framework to model Bitcoin. Okay, so here I'm going to briefly assume you have some small degree of familiarity with Bitcoin. So to model Bitcoin, obviously now the relevant resource is the computational power, or specifically the hash rate. The resource pool then specifies a hash rate for each identifier, each participant, if you like, at each time slot. Then we just allow each user one request to broadcast a block at each time slot. Okay, and then we have the oracle grant permission to broadcast a given block with probability proportional to their hash rate. Okay, so this gives us a really simple way of modeling Bitcoin, and in fact, it's a fairly simple model to fairly similar model to some of the models, existing models that use to model Bitcoin. But we'll see different models required for modeling proof of stake protocols and other kind of protocols. Okay, so this gives us a simple way to model Bitcoin. So what changes then if you want to model proof of stake protocols? So first, let's remind ourselves how proof of stake protocols work. So I mentioned briefly before, let's remind ourselves. So now at each point in time, a user's resource balance is their stake in the currency, right? It's the amount of currency they own. And with the proof of stake protocol, it's the user's stake that determines whether they can produce new blocks or send other kind of messages, right? A user's stake, though, the amount of currency they own, that depends on which transactions have taken place. So on the set of valid blocks, or more generally on the message state, right, on the set of delivered messages. So that means that a user's balance according to the top chain here, this is supposed to be a chain of blocks of transactions, that might be quite different than their balance according to the bottom chain there, right? So that means that a user's balance can now look different from the perspective of different users, right? So certainly we need a different framework than is usually used for modeling Bitcoin, at least for that reason. Okay, so one difference is that the resource balance depends on the message state now, right, which might be different from the perspective of different users. That's one difference. And then another fundamental difference, which really impacts the conditions in which the protocol can successfully operate, is that with the proof of stake protocol, the resource pool is known to all participants from the start of the protocol execution, right? While for a proof of work protocol, it isn't. Okay, so that's true because the resource pool is a function which tells you how each user's resource balance depends on the time slot of the message state. With a proof of work protocol, you don't know in advance how a user's hash rate will vary as a function of time. Right? You don't know how much Bitcoin mining will be happening in 5 years' time. Okay, with the proof of stake protocol, you do know in advance how a user's currency balance will vary as a function of the message state, right? As a function of a set of blocks. So that doesn't mean that you know in advance which users will be rich at later time slots, because you don't know which blocks will be broadcast, right? But as we'll see later on, the fact that the resource pool is known ahead of time means that proof of stake protocols can function in the partially synchronous setting, while proof of work protocols can't. Okay, so I'm going to call a variable determined if it's known to everybody from the start of protocol execution, and undetermined otherwise. What we just said is a fundamental difference between proof of work and proof of stake protocols is whether the resource pool is determined. Okay, so this differentiates proof of work protocols and proof of stake protocols. So proof of work protocols can't solve the Byzantine general problem in the partially synchronous setting, while proof of stake protocols can. And the result is more general than that, right? So it applies to any permissionless protocol in which the resource pool is undetermined. Okay, so that's a nice example of the framework functioning, I think. So I said before that we want to define a framework which allows us to prove general results of protocols that follow from simple properties of the resource pool and the permitter oracle. So this is one example. We'll see various examples there. And in fact, what we find is there are really just 3 or 4 fundamental properties which determine the conditions in which permissionless protocols can produce consensus. Okay, so whether the resource pool is determined is one, and then there are several others which I won't mention now for sake of keep things simple.
Can I ask a quick question?
Yeah.
So you also mentioned the asynchronous communication model before. Is it also possible to have a connection between the properties of the resource pool and the asynchronous communication model, as you showed?
If you're moving to from okay, so consensus won't be possible even in the partially synchronous setting if the resource pool is undetermined. If the resource pool is determined, then it becomes possible in the partially synchronous and the asynchronous, right? So you can, well, again, so long as you accept probabilistic protocols, and so long as less than. As long as the adversary always has less than a third of the total resource value.
Okay, thanks.
Okay, so that's, well, I've described everything in a pretty high level there. Okay, that's basically almost everything I want to say about the framework. I'm going to talk about results a little bit, but before I talk about results, we need one more pretty obvious definition. So here's a pretty obvious definition. So if you're working in the permissionless setting, then placing bounds on the power of the adversary now means limiting their resource balance, right? Rather than limiting the number of processes they control. Okay, so we let P be the set of processes and let PA be the processes controlled by the adversary. Well, then for Qn01, we'll say the adversary is Q bounded if their total resource balance is always at most a Q fraction of the total. Okay, so that's kind of just what you'd expect. So the adversary is half bounded if they always control at most half the total resource balance. Yeah. Okay, so let's take a look at the results then. So I'm going to go through various different results now. There'll be a mixture of sort of negative and positive results. Right? So basically, obviously, the negative results are results that you need, well, either this framework or at least some sort of framework to get. Interspersed, there'll be positive, like previous positive results. So you don't need any sort of framework to get the positive results, right? Okay. So the negative results are the new ones here. Okay, so our first negative result, so we'll consider the synchronous setting. Well, this also holds to the other partially synchronous and then asynchronous settings as well. But consider the synchronous setting and suppose that the adversary is in some sense non-trivial. Okay, so the adversary has non-zero resource balance. Well, then there's no deterministic permissionless protocol that solves the Byzantine general problem for a Q-bounded adversary. Okay, so that's in strong contrast to the permissioned case before. So all the results I mentioned before, they were all deterministic results, right? So now we get that the deterministic consensus isn't possible. You have to, if you want consensus, you're going to have to be probabilistic. There are some sort of technical things I'm sweeping under the rug here slightly because I haven't properly defined for you what I mean by a permissionless protocol. There are some sort of non-triviality conditions required here in order to get this. Okay? But I'm sweeping some of the technical details under the rug. Okay, but if you're talking about some non-trivial, interesting protocols, then you're going to have to consider the probabilistic case or the consensus here in the permissionless setting. Okay, so what follows then? I'm going to restrict attention to probabilistic solutions. Okay, so then what results do we get? Talking about probabilistic protocols. So remaining in the, again, sort of depend on whether we're in the synchronous or partially synchronous setting, whether we have digital signatures or not. Okay, so let's consider the sort of strongest case first. So let's imagine we're in the synchronous setting and we've got digital signatures. Okay, so the pertinent question then becomes, so for which Qn01, there exist permissionless protocols giving a probabilistic solution to the Byzantine general problem for a Q-bound adversary. So, so the positive result here was proved in the in what's called the Bitcoin backbone paper. This is the paper which first proved that Bitcoin operates properly. Published in 2015 or so. So in that paper, they considered the Byzantine general problem, and they showed that you do get a positive solution when Q is strictly less than a half. But the problem remains open for Q between half and 1. Okay. So that's the first sort of setting. That's in the synchronous setting when we have digital signatures. So next, let's consider the synchronous setting without digital signatures. So first of all, here it's interesting to go back to the permission setting in order to compare and contrast things. So when we consider the permission setting before, we always consider this setting where we have private channels. It's interesting to ask that if you don't have private channels, instead have broadcast, well then, so what happens in that case? Well, again, it depends on whether you have digital signatures or not. If you don't have digital signatures, then it's not that hard to show that in fact consensus then becomes impossible in the permission setting. Okay, so if you don't have digital signatures and you can only interact by broadcast, then there's a result which is, well, in some sense by Parsons Shee, but it's very similar, proof to an proof by Oken from 2005. So in the permission setting, you can't achieve consensus there. What happens in the permissionless setting? Well, we get a similar sort of negative result, supposing that Q is greater than or equal to half. Okay, so that's a negative result. But then again, there's a pre-existing positive result shown in the Bitcoin backbone paper 2015, which again shows that Bitcoin gives a positive solution when Q is strictly less than a half. So that doesn't require digital signatures. Okay, so lastly then, let's go on and consider the partially synchronous setting. So again, this is the setting where, well, various different ways of looking at it. You could say that there is a bound on how long it takes messages to arrive, but we don't know it. Or essentially, the equivalent way of looking at it is that there's a bound which happens sometimes. That's holds for unbounded periods, but also sometimes you're allowed unbounded network partitions. Okay, so the fundamental result in this setting is that probabilistic permission and consensus is not possible. This is the result that I mentioned previously when the resource pool is undetermined. Okay, so there's no permissionless protocol with undetermined resource pool. It'll be a probabilistic solution to the Byzantine general problem. So in particular then, that means proof of work consensus protocols can't work in the partially synchronous setting. Proof of stake protocols can though. So here you can get solutions even only if Q is strictly less than a third. Okay, so that's a sample of some results, and then there are a huge number of open questions here. So I haven't considered mobile adversaries yet. So we've considered settings here where the adversary controls a fixed set of participants. They're not able to corrupt people as the process unfolds. I considered various different settings in terms of how reliable communication is, but we didn't consider a situation where different processes have different clock speeds. We assumed we haven't considered contexts where message lengths are bounded and so on and so on. Okay, so there's lots of open questions. For now, I think I'll stop there. So thanks for listening.
Okay, excellent. Thanks a lot. I'll